Hello students, let me welcome you all to my 7th video on the chapter. Yes, it is phenols, right? That is 7th video on the chapter alcohols, phenols and ethers, right? In the previous discussion, we discussed something about the phenols, classification of phenols, nomenclature of phenols and methods of discussion, right? Now the today's discussion, we'll go for the physical properties of, yes, it is phenol. Physical properties of phenol, and of course we will go for, yes, it is boiling points of phenol, that is boiling points of phenols, right? That is boiling points of phenol. As far as phenols are concerned, they are characterized by OH group, which is polar. OH group is directly attached to benzene ring, and that is polar. Because of that, that phenol undergoes, intermolecular hydrogen bonding. Phenol undergoes intermolecular hydrogen bonding. Like this, this is what we call it as, this is phenol, yes, this is phenol, right? It will undergo hydrogen bonding with, yes, it is one more molecule of, yes, it is phenol, like this, right? Notice. And in the case of which, delta minus on the oxygen, delta plus on the hydrogen, and then it will attract this delta minus of oxygen, delta minus on the oxygen, delta plus of hydrogen. These are the two molecules of phenol, and positive part of this OH bond, that is attracting negative part of OH bond of the another molecule. Yes, thereby there is a intermolecular hydrogen bonding, and that will be continued. That is O. That is negative part of this. Yes, it is. This is one more molecule of phenol, right? And this is positive part of this molecule is attracting negative part of another molecule of phenol, and this is delta plus. The positive part of this will be attracting negative part of another molecule of phenol. Yes, yes, it is. And this is what we call it as intermolecular hydrogen bonding in phenols. Because of this intermolecular hydrogen bonding, there is a molecular association of phenol molecules. Therefore, boiling points of phenols will be greater than the corresponding hydrocarbons with almost the same molecular mass. For example, as far as the phenol is concerned, look at this. This is phenol, and its molecular mass is 94. You can calculate that. The molecular mass of phenol is 94. And the molecular mass of toluene, the corresponding hydrocarbon with almost the same molecular mass, that is what we call it as 92. The molecular mass of toluene is 92. And the boiling point of phenol is around 455 kelvins. This is the boiling point of phenol. Whereas boiling point of toluene will be around 384 kelvins. On the basis of that, I can say that the boiling point of phenol will be greater than corresponding hydrocarbon with almost the same molecular mass. Because of that, yes, it is, the phenols are having higher boiling points compared to the corresponding hydrocarbons with almost the same molecular mass. And that's because of the molecular association due to intermolecular hydrogen bonding in phenols. Molecular association due to intermolecular hydrogen bonding in phenols. Is that clear? So that is what we call it as boiling points of phenols. Okay. Now we'll see solubility of phenols, right? The next is what we call it as solubility of phenols under the physical properties of phenol, right? The solubility of phenols, right? Solubility of phenols. And so once again I tell you that as far as solubility is concerned, solubility with respect to water. One of the factors that decides the solubility of organic compound are two lower members of organic compounds in water is ability to undergo hydrogen bonding. If a molecule takes part in hydrogen bonding with water, that will be soluble in water. That's a general observation. In the case of influences, which will be responsible for its solubility in water, yes. And of course, this is OH bond that is capable of forming hydrogen bonding with water, yes. OH bond, can form hydrogen bonding with water, yes. That OH bond of phenol can take part in hydrogen bonding with water. Therefore, this makes phenol to be dissolved in water. This OH bond will take part in hydrogen bonding with water. Therefore, this forces, this influences phenol to be, yes, it is soluble in water. But in the case of phenol, we have one more, yes, it is component, that is one more part of the phenol, that is, yes, it is hydrocarbon part, yes. Look at that, there are 6 carbon atoms. The contribution of hydrocarbon part is very, very large. And of course, very big group it is it not? Because of that, and this is makes phenol not to be dissolved in water. OH group makes phenol to be dissolved in water. Benzene ring makes phenol not to be dissolved in water. And of course, two forces, two influences which will be acting in opposite directions. Because of that, phenol is sparingly soluble in water. Phenol is sparingly soluble in water. Because of these two factors, which will be acting in opposite direction. That is, hydrocarbon part is always hydrophobic, and it is doesn't have any affinity with water. Because of that, this makes phenol not to be dissolved in water, and that's why phenol is sparingly soluble in water. So this is what we call it as solubility of phenol in water. Yes. As far as phenols are concerned, phenol is colorless crystalline solid. Colorless crystalline solid. Color melting point. And as far as pure phenols are concerned, they are colorless crystalline solids. But when they are exposed to air, they acquire pink color or red color. The phenol acquires pink color or red color upon exposing to air. Phenol acquires pink color or red color upon exposing to air, because due to the formation of oxidized products of phenol, that is what we call it as benzoquinone. I am going to write this is benzoquinone. Yes. And this is one compound that is produced when phenol undergoes oxidation in presence of air. This is benzoquinone, and this will form a bond with, yes, it is hydrogen bond with, yes, it is phenol, like this. Okay, now, and this will form hydrogen bond with another molecule of phenol, yes, like this, and that is what we call it as, this is one more molecule of phenol, yes. Due to the formation of this complex, that phenols will have, yes, it is pink color. Yes, phenols acquire pink color upon exposing to air, and that is what we call it as the pink color of phenol is because of this particular complex, that is complex of phenols with what we call it as yes, it is benzoquinone. So this is what we call it as the properties and the physical properties of phenol. Right? So let us see that the chemical properties of phenol, right? Chemical properties of phenol, right? The chemical properties of phenols will be studied under two headlines. Chemical properties of phenol will be discussed under two headlines. One, it will be properties due to OH group. One, it will be properties of phenol due to, that is OH bond. That is properties due to the cleavage of OH bond. This is one discussion. This is one headline. That is properties of phenol due to the cleavage of OH bond. Another is properties due to the benzene ring. Properties due to the presence of benzene ring. These are the two types of properties that we observe in the case of properties of chemical properties of phenols. Under this headline, acidic property of phenol, right? A very important discussion as far as examination point of view, or you can say in the competitive exams also, that is acidic property of phenol. And in order to justify this acidic property, I'll go for some chemical reactions, that is action of metals. Action of metal, that is sodium metal, active metal, right? When phenol reacts with sodium metal, right? And this is phenol, okay, now when it reacts with sodium metal, right? And you are going to get hydrogen gas with the formation of sodium phenate, and of course you are going to get hydrogen gas. You know that OH bond has broken. This is OH bond has broken, right? To balance it, we have a H2 irodrinda, it is 2 here. ಇಲ್ಲಿ 2 multiply ಮಾಡಿದ ತಕ್ಷಣ ಇಲ್ಲಿ 2 multiply ಮಾಡಬೇಕು, ಆಗ 2 Ne ಆಗುತ್ತೆ, and this is what we call it as. So similar to that in the case of alcohols. Alcohols give hydrogen gas upon reacting with sodium metal. That is also the proof for the acidic property of alcohols. Here it is, the phenols react with sodium metal to give hydrogen gas. This is also a proof for the acidic property of phenols, right? So this is what we call it as one example. Apart from that, yes, one more evidence for the acidic property of phenols is when phenols react with NaOH, you are going to get, yes, it is sodium phenate, and of course along with the formation of, yes, it is water. So this is a base, right? And you are going to get a salt, therefore it should be an acid. This is simple acid base reaction, neutralization reaction, and you are going to get sodium phenate athwa sodium phenoxide. It's a salt, right? This is one more evidence for the acidic property of phenol. Apart from that, when solution of phenol is mixed with this, blue litmus, when solution of, yes, it is phenol is added with, yes, it is blue litmus solution, then it becomes red, okay? That is, it becomes red. That means phenol solution turns blue litmus red, and that is another evidence for the acidic property of phenol, right? So these are all the examples, right, for the acidic property of phenols, right? These are all the reactions where phenol is acting like an acid, yes? Okay, now, and because of that, now at this moment, it is very, very essential to understand that why that phenol is acidic. Now I'm going to give theory, right? That is the next discussion. Why that phenol is acidic, right? I'll go for one simple example for that. Yes, this is what we call it as, okay, OH, phenol, when it is dissolved in water. Yes, when it is dissolved in water, yes, you are going to get, yes, it is phenoxide, and of course H3O plus, and it releases H plus, and of course H plus will be taken up by H2O due to the presence of lone pair of electrons, and you are going to get phenoxide along with the formation of hydronium ion. This is a clear evidence that, you know, phenol releases H plus and gets converted to phenoxide. This is what we call it as phenoxide. Yes, this is what we call it as phenol, right? Okay, now? And of course, as far as acidity is concerned, ability of a molecule to release H plus ion, ability of a molecule to donate H plus ions to other substances, that is called as acidic, right? Okay, acidity we call it as, right? Athwa, that acidic strength we call it as, right? Why that phenol releases H plus ions to water? That's the question. Why that phenol releases H plus? Why that phenol donates H plus to water? That's the question. And for that purpose, you know, I'll go for one simple observation. Imagine if this chemical reaction takes place, A to B and it. This chemical reaction takes place because B is more stable than A. B is more stable than A. This is a common observation. A is less stable than B. Then only chemical reaction takes place. Otherwise, chemical reaction does not take place. Right? That you remember. Hagadre, that phenol gives H plus to water and becomes phenoxide. Phenol gives H plus to water and becomes phenoxide because phenoxide is more stable. Phenoxide is more stable than phenol. A gives B. Why? Because B is more stable than A. Phenol becomes phenoxide. Yake? Because phenoxide is more stable than phenol. Because of that, phenol is converted to phenoxide. In doing so, it has to release H plus ion. If it wants to become phenoxide, it has to donate H plus to water. That makes phenol to be acidic. That makes phenol to be acidic. Okay, na? Next question is why phenoxide is more stable than phenol? Yes. Phenoxide is more stable than phenol. That's why it donates H plus to water and becomes acidic, right? Fine. Why phenoxide is more stable than phenol? Why that phenoxide is more stable than phenol? That's the question, is it not? For that purpose, you know, here we have an answer for that, right? And I can explain it on the basis of resonance structures of, yes, it is phenol and phenoxide. Yes. Now we'll go for the resonance structures of phenol first, right? We'll go for the resonance structures of phenol, right? Resonance structures of phenol. We'll see that. Resonance structures of phenol, right? First, we'll see that. Look at this phenol, yes. Because you already know how to write the resonance structures in first PUC, right? It is a phenol, yes. There is a conjugation between pi electrons of benzene and lone pair of electrons of oxygen. Because for resonance effect to take place, you know, there should be a conjugation between lone pair of electrons and pi electrons. There is a conjugation. Therefore, pi electrons, lone pair of electrons will be moving towards benzene ring, and in that case, you know, yes, it is pi electrons will be shifted over. Yes, it is benzene, carbon atom of this, and because of that, you know, we have here one resonance structure. Yes, pi electrons or lone pair of electrons are moving towards benzene. Therefore, single bond is converted to double bond. Oxygen has lost electrons and therefore it requires positive charge. And of course, this is H. And pi electrons are shifted over here. Therefore, it becomes negative charge. And this is what we call it as one particular. Yes, it is resonance structure. And look at this in the resonance structure. There is a charge separation. Creation of plus and minus is produced. That is, there is a charge separation with positive charge on the oxygen. Look at this. First of all, oxygen is itself electronegative. Oxygen atom is itself electronegative. And it acquires positive charge. Andre, all the sigma electrons are moving towards, all the sigma electrons are moving towards oxygen, and OH bond becomes weak. And that makes it to release hydrogen in the form of H plus. And you continue that resonance structure. Look at this. Pi electrons, these electrons will be shifted like this, and this will be shifted like this. if I shift the electron pair over the atom, this is over the atom, it will get negative charge. If I shift the electron pairs between the atom, one extra bond is produced. That you have to observe. Yes, while writing resonance structures. Look at this. Ega, continue that. Yes, it is. This is what we call it as delta plus positive charge. And I shifted here double bond, it will be minus. Continue that. Yes, it is. Continue that. Yes, it is. You are going to get one more resonance structure. Yes. So this is double bond OH plus, right? And it is minus now. And double bond, and of course double bond. Now shift like this. It will be like this. And of course you are going to get one more resonance structure. Yes. The positive charge is neutralized. In the neutralization, this double bond is converted to single bond. OH. Double bond, and double bond. Yes. Okay, now you can find here. Yes, it is. The resonance hybrid you can find, and of course resonance hybrid can be obtained by mixing all these resonance structures, right? And this is what we call it as, yes, it is positive charge in the benzene ring, right? Sorry, negative charge in the benzene ring, right? Okay, now that is negative charge in the benzene ring, right? Yes, and here single bond, and of course partial double bond character, and of course here it is OH, and it becomes delta plus. Okay, so delta plus, and it will be delta minus. This is what we call it as, yes, it is resonance hybrid of, yes, it is phenol. And in all these resonance structures, you can find there oxygen is carrying positive charge, and that is what we call it as the molecule becomes unstable, because if positive charge is there, the sigma electrons are moving towards oxygen, the OH bond becomes, yes, it is, OH bond becomes, yes, it is weak, and that makes it to release hydrogen in the form of H plus. Apart from that, resonance leads to charge separation. If the resonance leads to charge separation, that makes molecule to be unstable. And at the same time, if I say resonance, if I observe the resonance structures of phenoxide, resonance structures of phenoxide ತಗೊಂಡ್ರೆ, resonance structures of phenoxide ತಗೊಂಡ್ರೆ, right? Resonance structures of phenoxide ತಗೊಂಡ್ರೆ, look at this. Yes, this is ಇದು first phenol ತಗೊಂಡಿದ್ದೀನಿ, ಈಗ phenoxide ತಗೊಂಡಿದ್ದೀನಿ, right? Okay na? If I write the resonance structures like this, this will be shifted like this, it will be shifted like this, and of course you are going to get first resonance structure. Yes, okay na? ಈಗ ಏನಾಗುತ್ತೆ, single bond becomes double bond, it will get minus charge, and of course double bond. You shift like this between and over the carbon atom, you write one more resonance structure. Yes, yes, it is double bond, right? And here it is minus, here it is double bond, it is double bond, right? Continue that. Yes, it is. You can write one more resonance structure. Yes, right? And this is minus, and of course double bond. Here it is double bond, and it is double bond, right? Haga continue ಮಾಡಿ ಇನ್ನೊಂದು resonance structure ಬರೀಬಹುದು. Yes, it is. And you are going to get, yes, it is, right? Double bond, and double bond. It is O minus. Look at this. In the case of phenoxide, you don't find any charge separation there. You don't find any charge separation there. Instead, the negative charge on the oxygen is delocalized. Negative charge is dispersed throughout the molecule. ನೋಡಿ, ಇಲ್ಲಿದ್ದು negative charge ಇಲ್ಲಿಗೆ ಬರುತ್ತೆ ಅಂದ್ರೇನು? The negative charge on the molecule is on the oxygen is dispersed. The negative charge on the molecule is dispersed throughout the molecule. ಆಗೇನಾಗುತ್ತೆ? The negative charge on the oxygen decreases, and that makes that delocalization of negative charge makes the phenol molecule more stable with no charge separation. The negative charge disperse ಆಗಿದೆ ವಿನಃ no creation of plus and minus. But here it is a creation of plus and minus takes place. Therefore phenol is unstable. Here there is a charge separation. Here there is no charge separation. Here positive charge is created on the oxygen, but positive charge is not created on the oxygen. Because of that, phenol is less stable, phenoxide is more stable. ಯೋಚನೆ ಮಾಡಿ ಈಗ. If phenoxide is more stable, you can write resonance hybrid also. Hybrid, right? Yes, it is. Resonance hybrid ಅಲ್ಲಿ ನೋಡಿ. Yes, it is. This is delta minus. Yes, it is. Oxygen ಮೇಲೆ ಕೂಡ delta minus ಇದೆ, right? So this is, but ಇಲ್ಲಿ ಏನಾಗಿದೆ? ಇಲ್ಲಿ oxygen ಮೇಲೆ ಏನಾಗಿದೆ? ಇಲ್ಲಿ delta plus ಇದೆ, ಇಲ್ಲಿ delta minus ಇದೆ. ಅಂದಾಗ here there is a charge separation, here there is no charge separation. Because of that, yes, it is. That is phenoxide is more stable than phenol. ಹಾಗಾದ್ರೆ ನಾನು ಹೇಳಿದ್ನಲ್ಲ, If phenoxide is more stable than phenol, then phenol is trying to become phenoxide. In that process, phenol releases H plus, and of course that's why phenol is acidic. That's why phenol is acidic. Agboda? Yes. So that is what we call it as acidic nature of phenol, right? At this moment, yes, illondu resonance structures of phenol alli ಸ್ವಲ್ಪ ನೋಡ್ಕೊಂಬಿಡಿ, ಮುಂದೆ ಅದು ಅನುಕೂಲ ಆಗುತ್ತೆ. ಈ resonance structures ಅಲ್ಲಿ ನೋಡಿ, and because of this resonance you will find negative charge on the ortho position. ಇದು ortho position ತಾನೆ, with respect to weight, this is ortho, this is para, ಹೌದಾ, this is ortho. You can find negative charge on the ortho and para positions. ಅಂದ್ರೆ OH group when it is attached to benzene ring increases electron density at ortho and para positions. When OH group is attached to benzene ring, it increases electron density at ortho and para positions. ಹಾಗಾಗಿ ಈ ಕಾನ್ಸೆಪ್ಟ್ ಅನ್ನು ನಾನು ಎಲೆಕ್ಟ್ರೋಫಿಲಿಕ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಷನ್ ರಿಯಾಕ್ಷನ್ಸ್ ಅಲ್ಲಿ ಯೂಸ್ ಮಾಡ್ಕೊತೀನಿ. ಹಾಗಾಗಿ ಇದನ್ನ ಈಗಲೇ ನೋಡ್ಕೊಂಬಿಡಿ. So this is what we call it as resonance structures of phenol and phenoxide, and explanation for the acidic nature of phenol. Yes, explanation for the acidic nature of phenol. Effect of substituents on acidic strength of phenol. Two kinds of substituents you will come across, that is electron releasing groups and electron withdrawing groups. You know that. What is the effect of electron withdrawing groups on the acidic strength of phenol, and what is the effect of electron releasing groups? Now that we'll see, right? And of course, as any influence, right? As far as phenol is concerned, if any influence, any substituent that stabilizes phenoxide, that increases acidity of phenol. If any influence that destabilizes phenoxide, that will decrease the acidic strength of phenol. ಯಾವುದೇ ಒಂದು ಸಬ್ಸ್ಟಿಟ್ಯೂಯೆಂಟು ಫಿನಾಕ್ಸೈಡ್ ಸ್ಟೆಬಿಲಿಟಿನ ಜಾಸ್ತಿ ಮಾಡಿದ್ರೆ ಅಸಿಡಿಕ್ ಸ್ಟ್ರೆಂತನ್ನು ಜಾಸ್ತಿ ಮಾಡುತ್ತೆ. ಯಾವುದೇ ಒಂದು ಸಬ್ಸ್ಟಿಟ್ಯೂಯೆಂಟು ಫಿನಾಕ್ಸೈಡ್ ಸ್ಟೆಬಿಲಿಟಿನ ಕಡಿಮೆ ಮಾಡಿದ್ರೆ ಅಸಿಡಿಕ್ ಸ್ಟ್ರೆಂತನ್ನು ಕಡಿಮೆ ಮಾಡುತ್ತೆ. ದಟ್ ವಿಲ್ ಸಿ ದಟ್ ಐ ಆಲ್ರೆಡಿ ಸೆಡ್ ದಟ್ ಈಸ್ ವಾಟ್ ವಿ ಕಾಲ್ ಇಟ್ as, this is what we call it as phenol. Yes, this is phenol plus H2O, right? I already written that. We'll see once again. So this is phenoxide. Yes, that is phenoxide plus H3O plus something. Okay, na? Right? Imagine if I connect one electron withdrawing group like this, that is G anta itಕೊಳ್ಳಿ. Yes, G1 group, that is say for example one nitro group. G is equal to nitro group, or it can be cyano group. Yes, it can be SO3H group. Yes, it can be CHO group. These are all electron withdrawing groups, right? That is NO2 group, that is nitro group, CN group, SO3H group, and CHO group. They are all electron withdrawing groups. When electron withdrawing groups are attached to the benzene ring, right? When electron withdrawing groups are attached to the benzene ring, that will be present here also. Then is it not? Illu kuda iruttadu. Hauda? If electron withdrawing group is connected, ಏನಾಗುತ್ತೆ? It withdraws electrons towards it ಅಂದಾಗ the negative charge on the oxygen decreases, right? The negative charge on the oxygen decreases, right? If negative charge decreases, ಏನಾಗುತ್ತೆ? Stability of phenoxide increases, because this negative charge will be further dispersed throughout the molecule. ಈ ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ ಏನಾದರೂ ಆಕ್ಸಿಜನ್ ಮೇಲೆ ಕಡಿಮೆ ಆಗುತ್ತೆ ಬಿಕಾಸ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ ವಿಡ್ರಾಯಿಂಗ್ ಎಫೆಕ್ಟ್. ಯೋಚನೆ ಮಾಡಿ, ಅಕಸ್ಮಾತ್ ನೆಗೆಟಿವ್ ಎಫೆಕ್ಟ್ ಜಾಸ್ತಿ, ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ ಆನ್ ದಿ ಆಕ್ಸಿಜನ್ ಜಾಸ್ತಿ ಆದ್ರೆ ಏನಾಗುತ್ತೆ ಗೊತ್ತಾ? ಈ ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ ಇದೆಯಲ್ಲ, ಈ O- ಇದೆಯಲ್ಲ, ದಟ್ ಅಟ್ರಾಕ್ಟ್ಸ್ H ಪ್ಲಸ್ ಅಂಡ್ ರಿವರ್ಸಸ್ ದ ರಿಯಾಕ್ಷನ್. ಇದ್ರ ಮೇಲೆ ಏನಾದರೂ ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ ಜಾಸ್ತಿ ಆಗ್ಬಿಟ್ರೆ ಆಕ್ಸಿಜನ್ ಮೇಲೆ, ಅದು H ಪ್ಲಸ್ ಅನ್ನು ಅಟ್ರಾಕ್ಟ್ ಮಾಡಿ ರಿಯಾಕ್ಷನ್ ರಿವರ್ಸ್ ಮಾಡ್ಬಾರ್ದು. ಆಗೇನಾಗುತ್ತೆ? ರಿಯಾಕ್ಷನ್ ರಿವರ್ಸ್ ಆಗುತ್ತೆ ಅಂದ್ರೆ ಏನು? ಅಸಿಡಿಕ್ ಸ್ಟ್ರೆಂತ್ ಡಿಕ್ರೀಸಸ್. ಬಟ್ if electron withdrawing groups are connected, ಏನಾಗುತ್ತೆ? The negative charge on the oxygen is dispersed throughout the molecule. Negative charge on the oxygen decreases. Therefore, stability of phenoxide increases. Therefore, electron withdrawing groups are going to increase. Acidic strength increases, right? And of course, because of that, all nitrophenols are more acidic than phenol. All nitrophenols are more acidic than phenol. All nitrophenols andre we have, yes, it is that is paranitrophenol, more acidic than, yes, it is orthonitrophenol, more acidic than, yes, it is metanitrophenol, yes, more acidic than phenol. Look at this, all, yes, it is nitrophenols are more acidic than phenol, because in nitrophenols we have, yes, it is electron withdrawing group. Yes, when nitro group is at the para position, the extent of delocalization of electron pairs will be maximum, and that's why that paranitrophenol is more acidic than orthonitrophenol. Illu kuda delocalization ide, illu kuda there is a delocalization of electron pairs, but when nitro group is at the para position, that extent of delocalization of electron pair is maximum. Paranitrophenol is more acidic than orthonitrophenol because your ortho is more acidic than meta, because when the nitro group is at the meta position and OH group will not be affected by the Ac's nitro group, because OH group, the OH group of the lone pair of electrons on the OH group will not be in resonance with nitro group at the meta position. Because of that, electron withdrawing effect is less here, and therefore it is less acidic than this. And of course, all these three are nitrophenols. They are more acidic than phenol, and that is what we call it as, yes, it is acidic strength of phenol. Okay, now, so that is what we call it as the effect of electron withdrawing groups. Now, if I connect electron releasing groups, right? If I connect electron releasing group like R, if I connect electron releasing groups like R, when electron releasing groups are connected, yes, when electron releasing groups are connected, like, okay na, nodi, again it is releasing electrons towards benzene ring, it is releasing electrons towards, yes, it is phenol, okay na, it is releasing electrons towards benzene ring, right? Again agate electron density on the oxygen increases. It releases electrons, then electron density on the oxygen increases. Again agate the negative charge on the oxygen increases, and that makes it attract H plus. Reaction is reversed. Therefore, electron releasing groups will destabilize phenoxide ion. Electron releasing groups will destabilize phenoxide ion. Therefore, acidic strength decreases. Therefore, electron releasing groups, right, decrease. Acidic strength of phenol, decrease acidic strength of phenol. Therefore, all cresols are less acidic than, yes, it is phenol. Athava phenol is more acidic than cresols. In the case of cresols, we have one electron releasing, that is CS3 group, right? For example, this is phenol, yes, and this is phenol, yes, more acidic than, yes, it is, and it is CS3 group, right? Metacresol, and then it is more acidic than, and it is paracresol, yes, and more acidic than, yes, it is orthocresol. Then it is more acidic than orthocresol, yes. Okay, now this I remember by using one mnemonics, that is PMPO, Prime Minister's Personal Officer. Prime Minister's Personal Officer. P stands for phenol. Yakandre niಮಗೆ ಗೊತ್ತಿದೆ already. Phenols are more acidic than cresols ಅಂತ ಹೇಳಿ. So phenol, metacresol, paracresol and orthocresol. So ನಿಮಗೆ ಇನ್ನೂ reason ಬೇಕಂದ್ರೆ ನೋಡಿ, when any group is at the meta position, it will not affect on the OH group. Yes, its electron releasing effect will not be affected by OH group when it is at the meta position, whether it is electron releasing group or electron withdrawing group. And your CS3 group releases electrons by inductive effect. It is far away from this. Therefore, electron releasing effect is less compared here, because it is very closer to, yes, it is OH group plus I effect. Yes, okay na. Because of that, this is what we call more acidic than this. So this is the acidic strength of cresols. So cresols are weaker acid than phenols. Athwa phenol is more acidic than cresols. So that is what we call it as effect of electron releasing groups on the acidic strength of phenol. Agboda? Yes. ಈಗ ಇಷ್ಟೇನೆ, electron withdrawing groups will increase acidity of phenol by increasing stability of phenoxide, whereas electron releasing groups decrease acidic strength of phenol by decreasing stability of phenoxide. Ashtene, okay na? Let me compare acidic property of phenol with that of the water, with that of the alcohol. That is acidic strength of phenol versus alcohol, right? Acidic strength of phenol versus alcohol. Both are acidic. Out of these two, which is more acidic, which is less acidic, that we'll see, right? So this is phenol. It releases H plus and you are going to get phenoxide. This is phenoxide, yes. Okay, na? Idu nimage gottiro vichara. Already you know this, right? This is phenoxide, yes. Imagine if I take ROH, when it comes in contact with water, right? You are going to get, it releases H plus and becomes RO minus, and of course H3O plus, right? This is what? Alcohol, and this is alkoxide. This is alkoxide. This is phenoxide. Imagine, one important aspect is, that is out of these two, right? In the case of this phenoxide, yes, this oxygen is directly attached to the sp2 hybridized carbon. Yes, O minus is directly attached to the sp2 hybridized carbon. In the case of phenol, in the case of alcohol, O minus is directly attached to the sp3 hybridized carbon. Yes, ಇದರಲ್ಲಿ sp2 hybridized carbon ಇದೆ, ಇದರಲ್ಲಿ sp3 hybridized carbon ಇದೆ. Because out of these two, which is more electronegative? sp2 hybridized carbon atom. Therefore, because of that high electronegativity of sp2 hybridized carbon atom, because of that high electronegativity of it is sp2 hybridized carbon atom in phenol, that OH bond becomes more polar. ಎಲ್ಲ electrons ಈ ಕಡೆ ಬಂದ್ಬಿಡುತ್ತೆ sp2 ಕಡೆಗೆ, ಯಾಕಂದ್ರೆ it is more electronegative than that is carbon atom of alcohols. ಅಂದಾಗ OH bond is more polar and therefore hydrogen will be liberated in the form of H plus. Here in the case of alcohol, that carbon atom is sp3 hybridized, that is less electronegative than phenol, and that is one reason. Second reason is, look at this. Second reason is, in the case of phenol, you are going to get phenoxide, and that is resonance stabilized. But here in the case of alkoxide, we don't find any resonance structures. You cannot write any resonance structures to the alkoxide because there is no conjugation. There is no conjugation, right? We don't find any conjugated system here. Because of that, no resonance structures here. And therefore, phenoxide is stabilized by resonance, but alkoxides are not stabilized by resonance. Therefore, phenoxide is more stable than alkoxide. And therefore, phenol is more acidic than, yes, it is alcohol. Phenol is more acidic than alcohol. As a proof for that, when alcohol is mixed with NaOH, no reaction. As a proof for that, when alcohol is mixed with NaOH, no reaction. When phenol is mixed with NaOH, you are going to get a reaction, and that is what we call it as sodium phenoxide salt you are going to get. So this is one evidence that alcohols do not react with sodium hydroxide, whereas phenols react with NaOH to give sodium phenoxide. This is the reason. This is the evidence to say that is phenol is, yes, it is more acidic than, yes, it is alcohols, right? That is one more discussion. Now at this moment, I want to highlight one more important aspect. That is, no doubt, phenol is acidic. Phenols are more acidic than alcohols. That is doubt ಇಲ್ಲ. But when phenol reacts with sodium, when phenol is mixed with sodium bicarbonate or sodium carbonate, there is no reaction. Why should I go for this sodium bicarbonate? Because any acid for that matter, when an acid reacts with sodium bicarbonate, you are going to get carbon dioxide. You are going to get carbon dioxide gas. When an acid reacts with sodium bicarbonate, you are going to get carbon dioxide. For example, carboxylic acids, when they react with sodium bicarbonate, you are going to get, yes, it is carbon dioxide. But in the case of phenol doesn't give, yes, it is carbon dioxide when it reacts with, yes, it is sodium bicarbonate. If it is acidic, if the acidic strength of phenol is similar to that of carboxylic acids and HCl, it would have liberated, yes, it is carbon dioxide. But there is no reaction between phenol and sodium bicarbonate, because, and as far as phenol is concerned, and of course as far as phenol is concerned, no doubt it is acidic, but it is, yes, it is weak acid, weaker than carbonic acid. Phenol is weak acid, but it is weaker than carbonic acid. What is carbonic acid? It is nothing but carbon dioxide plus water. It is nothing but carbon dioxide plus water. That is carbonic acid. The acidic strength of phenol is, yes, it is, acidic strength of phenol is, that is less than that of the carbonic acid. Therefore, it does not give carbon dioxide. It does not give carbon dioxide because it's a weak acid and it is weaker than carbon dioxide. It's a strong acid. Therefore, weak acid never displaces strong acid from the compounds. Or the weak acid never displaces carbon dioxide from the compound. Therefore, phenol is weak acid, never displaces carbon dioxide from, yes, it is sodium bicarbonate, and it is weaker than carbonic acid. And of course, why that phenol is weaker than carbonic acid, and all these things, they are all beyond the scope of this text. You can, yes, it is, ask me separately for the test acidic property of phenols. Now at this moment, under the headline, properties due to the cleavage of OH bond, I'll go for one more chemical reaction, that is action of zinc. Action of zinc, right? One more chemical reaction, that is action of zinc, right? This is also a very important reaction. When phenol reacts with zinc metal, right? This bond will be broken and you are going to get zinc oxide along with the formation of acetals, and this is what we call it as benzene. This is what we call it as benzene, right? Okay, na? So you can say that is ಇದು ಬರೆದಿದ್ರು ಕೂಡ ಪರವಾಗಿಲ್ಲ, ಏನು ತೊಂದರೆ ಇಲ್ಲ. ದಟ್ ಇಸ್ ನಿಮಗೆ ಅರ್ಥ ಆಗಲಿ ಅಂತ ನಾನು ಬರೆದಿದ್ದೀನಿ. H is connected to benzene, O is connected to Zn. We are going to get, this is what we call one more reaction. Apart from that, here we have one more discussion, that is acylation of salicylic acid. And as per your NCERT textbook, acylation of salicylic acid, right? As far as salicylic acid is concerned, we have here, this is salicylic acid, one of the phenols. This is 2-hydroxy benzoic acid. This is 2-hydroxy benzoic acid. This is 2-hydroxy benzoic acid. That's salicylic acid. This is salicylic acid. When it reacts with acetyl chloride, acetic anhydride. Acetic anhydride. This is acetic anhydride. In presence of concentrated sulfuric acid. In presence of concentrated sulfuric acid. Yes, look at this. And I am discussing this particular reaction under the headline, due to the cleavage of OH bond. And OH bond will be broken like this. OH bond will be broken like this. You are going to get CH3COOH. And CH3CO group is connected to oxygen. And thereby, you are going to get one useful compound, that is, yes, COOH, and it is O. COCH3 will be connected to this, C double bond O, and CH3 plus CH3, C double bond O, OH. So this is what we call it as aspirin. This is what we call it as aspirin. Okay, now this is what we call it as aspirin. Okay, now ASPIRINE. And of course, this is also, yes, it is, IUPAC name of it is 2-acetoxy benzoic acid. 2-acetoxy benzoic acid. Benzoic acid. Athwa acetyl salicylic acid. It can also be given a name. Acetyl salicylic acid is another name to that particular aspirin. 2-acetoxy benzoic acid. Athwa acetyl salicylic acid. Acetyl salicylic acid. So this is what we call it as properties of phenols due to the, we'll see the properties due to benzene ring. Properties of phenol due to benzene ring. So that's all about properties of phenols. Thank you.